I got 8:12. We're gonna get started. Okay. All right. So I think I'm recording this second session. We're just gonna, today's day one, so we're just continuing. Um, as you know, I started with the syllabus, some motivation, and now we're going over some examples of a library called Transformers from Huggingface. I'm just showing you guys what we can do. We can download large models, pre-trained models, and we're just doing inference. No training, nothing like that so far. And then I'll try to wrap up today with just this PDF with some of the terminology that we can use in very deep neural networks, right? So we want to get used to it. All right, so let's look at another example. So the next example in this sequence is going to be BART. So this is another model, as I said. The A is significant there. But this is actually called a distilled BART. So that has meaning also. That's something that we want to become familiar with. Okay, and so I'll talk a little bit about that. Yeah, and so we're going to do a very similar example using pipeline, but if you notice here, it's doing summarization, right? So this starts to get, as you can see, more like a GPT, right? So because it's a generative model of text, so you can see where that BART variant implies that this can do text generation. All right, so what is distillation? This is an important concept. So this is actually something that for instance, is a recommendation that I would give you guys to use distilled models, for instance, in your homework assignments. And what do I mean by that? Maybe you want to use a GPT 3.5 Turbo, let's say, right? So a very large model. That's going to be, I don't know, let's say 10 gigabytes, something. It's just an example. That's obviously going to be pretty large to run. So whenever you're fine-tuning it or you're doing things like that, you're going to run out of memory. It's going to give you all kinds of problems depending on your setup, right? But you really want to use that GPT 3.5 Turbo because you know it's really good. So instead of using that base model, what you can do is probably find a distilled GPT 3.5 Turbo. Okay? So that's, it was like a paper, something that was created, and it's a process called distillation, which essentially you train the large model, right, which all the layers, all the weights is very powerful, but then once it's trained, you create a smaller version of it. Like the architecture is smaller, it'll have fewer weights. And that model, if you trained it on the original data, for some reason, it wouldn't learn the same way. So what you do instead is that the distilled model is trained by getting data from the original model. Do you see that? So essentially the concept is that you're distilling the knowledge of the big model into a smaller model. That's the process of distillation. Again, we'll come back to that idea, but for now, that's the main, it has been proven experimentally that works better. So, you have a really large model, you give it all the data, it learns really well. If you were to build a smaller architecture and train it on the original data, for some reason, it just doesn't learn as well. However, if you distill it from this one to this one, then you may get a better result. This has been proven experimentally. So the advantage of that is that you get a good model, but that also runs with less memory. So for your case, I know in the past when we've done homework, people, maybe I was using GPT-2, a student ended up using a distilled GPT-3, and it worked really well. Does that make sense? So you have to find those trade-offs, okay? And distillation, as I said, it's another concept that we will cover later, but that's the gist of it, all right? So you can see that here. So I'm going to be using a distill BART. The CNN is probably where the text is coming from and so on, like the data set. All right, so let's try this one out. Okay, so I'm going to go here. So from transformers, I'm going to import several things: auto model, pipeline. Definitely something we need is the BART tokenizer. We have this BART for conditional generation. So all of these things are pre-built or preset encapsulations, right? So this idea that you're adding individual heads for some task that you want to accomplish. The BART config, this is something that we will need later on, especially when we're fine-tuning. We're going to have this notion of a configuration file, and we have all of our parameters there. Okay, so that ran nicely. Now I'm going to go ahead here. Okay, and so I'm going to use pipeline again, as I used before. I want to use pipeline, and in this case, I want to use it, for instance, in the context of summarization. Okay, so again, what that means is there's the embedding layers, and then there's going to be some kind of additional layers that are added to this BART model. Okay, so you can see I'm going to have a model, a tokenizer. I'm going to specify that I want BART for conditional generation, and then from pre-train I can select the version that I want to use, which in this case is a distill BART and the corresponding tokenizer, which remember has the mapping from the words to the embeddings. Okay, so those are the two things that we get. I don't know if you guys remember in 520 when we did an LLM, there were two passes, right? There was the first pass just to get the dictionary of the words, if you remember, and then we would use that in the model. So that's why we have two things. So now here I have the pipeline. I specify that I want a summarization. I have my model and the tokenizer that I just downloaded, and I just call it NLP. Okay? So what I want is I want to give it some text, and it's going to summarize it. Okay? That's what it's been trained to do. Now, obviously, this may not be the best summarizer. There's certainly better ones, right? But this is just an example. And you can look it up. You can look up a better one on the Huggingface hub. So as you can see, these models are large. You can see it takes a little bit for them to be downloaded. Look at the sizes, right? And that's, that's the world of very deep learning models, unfortunately. And I'm not using my GPU. I should have changed the runtime to GPU. Actually, I forgot about that. So I might change it in the next example. Okay, so I think it finished. I had a green check here. Okay. So now let's go ahead and see. This is going to be the text. And it's just some text on aviation. And essentially what I'm going to do is I'm going to give this text to this NLP pipeline, and it's going to summarize it, for us, right? So that's the example. So we can print it. So there it is. And I'm going to add a few more cells here. And now we can proceed to summarize. Yeah, so I should probably switch to the GPU. But you can see aircraft includes fixed wing and rotary wing types, morphable wings, wingless lifting bodies, and lighter than aircraft such as hot air balloons, airships, and it goes on to summarize a little. Do you see that? So this is just one of many applications of these models, okay? But so today I'm really just focusing on showing you the library and showing you kind of the approach that Huggingface has taken, this idea of encapsulation. They do have this pipeline is you'll see it a lot. The fact that we download the models from the Huggingface hub, we always download a model and tokenizer, and then we have multiple applications for this. So it's convenient, but it has sometimes less flexibility, right? You can see how we're kind of stuck to, all right, I want to do a summarization, I want to do a classification, what else can I do, all right? So if you want more flexibility, you have to get more into the coding aspect of it, okay? But there's a lot that we can do. Certainly one thing that everyone may want to do is take an LLM and just fine tune it. So for that, taking the Huggingface approach should be enough, all right? All right, so now that was one example. Any questions? Remember, we're just doing inference. This did a summarization. We can look up what a BART is. So I can say the BART paper and just kind of look at the specs of it. So 2019, that looks about right. Oops. This one says denoising sequence to sequence pre-training for natural language generation, translation, and comprehension. So you can see back then, 6 years ago, right? They were trying, and this was from Facebook, right? They were still focusing on tasks. Okay, natural language generation, so like a GPT, right? Comprehension, the understanding. So here it says Facebook. So they say we present BART, a denoising autoencoder. So we'll cover this, an autoencoder for sure. We'll build one of these from scratch. It's like when we covered GANs last semester, there's some ideas there, but an autoencoder is essentially a neural net, right? A deep neural network that takes an input and produces the same input. Do you see that? So for instance, I have, a vector of size an image. An image is actually a great example, right? So I have an image of a cat, and then it goes to the next layer, and every layer gets smaller. So it's compressing it until we get to a point where it's, it was initially, let's say, 784. It is now 100. You see that the vector has been compressed. And then what do you do from there? In the autoencoder, you decompress it. So now, kind of symmetrically, you start to scale up all the way up to 784 again. Do you guys see that? And so we go from 784 to 784, compress it, decompress it. That's all that an autoencoder is doing. So then that seems almost like pointless, right? Like why start, have an image and then create the same image. But this idea of denoising, sometimes you want to learn, compress the image, filter something out that doesn't have noise. So then you start adding elements to the autoencoder. Also, like for anomaly detection, the fact that when you compress it, the middle layer is a representation almost of the original image. So that has some semantic meaning that can be used, and so on. So we'll see applications of that later on, but that's essentially what an autoencoder is. In terms of just a deep neural net, a vector goes to the next layer, which is smaller, then the next layer, which is smaller. Remember, from layer to layer, we learn it's just a matrix multiplication, and you define how small you want to get, and that's the compression, and then the decompression going back up to the original image. Any questions about that, guys? Yeah, go ahead, please. Aha. ChatGPT. Yeah, of course. No, they're not using a BART. It's a GPT. So the way that I would answer that question is, it's a GPT that was pre-trained, then it was fine-tuned, then then you use reinforcement learning. So we don't even know essentially how it learned it. But that's the solution. So reinforcement learning through human feedbacks is a concept we'll learn later. It came about because somebody was trying to train a robot to dance salsa. So the idea is, how do you train a robot to dance salsa? What's the loss function for that? Do you know what I mean? How do you code mathematically that this is good salsa dancing? So they couldn't figure it out. So they said, instead of doing that, let's invent this thing called reinforcement learning. We have a model, we just tell it to randomly dance, and then give us 3 clips of your dancing. A human will look, for now, later we can use a bird, right? But a human initially looks at the 3, and we can look at 3 and say, well, I mean, this is maybe this one, but that little feedback of maybe this one out of the 3 is enough for the weights to be updated. So then the next time, right, it's going to tend towards that. And maybe now it does 1,000 iterations on its own. Then we get, again, 3 clips. Maybe it's a little bit better. And then we say, maybe this one, and so on. And you just keep doing that. So now to answer your question, you're saying, how does it summarize well? Same idea. You just say, take some text and make it more compressed, right? And then generate 3 of those. I'm going to read all 3, and I'm going to say, this one. Do you see that? And then that feedback is what goes back into the GPT, and then you keep doing that until eventually, guess what? The summarization starts to get better. This was the key trick that solved ChatGPT. So they had the pre-training. You can see here historically, right? We got a transformer. Then you've seen we've got a BERT. We've talked about GPTs, but they're still not very good. You asked the question summarization. We're in 2019. The best we have is a BART, right? But it's still not great. It's still not gonna cost this wow factor, right? Like in 2022. So the solution was they hired, and the thing is, pre-training is massive. But once you get into fine-tuning and reinforcement learning, you actually don't need that much data, right? In relative terms, compared to the trillions of tokens that you needed, right, for the initial pre-training. And so they just hired people. They hired, a lot of people to review the answers. And by reviewing the answers and providing this feedback, they realize, hey, we don't need a BART. The GPT is good enough. Somehow, magically, let's say, the GPT can do it as long as it gets that feedback. That's the thing that's amazing about GPTs. It's still kind of the original architecture as in 2017. Very little has changed, but the methods that they used are what was amazing. So for instance, today, I heard the other day, you know how there's financial planners and people that do finance reports and all of that, right? And that costs a lot of money. People, companies go in and then they produce these very fancy reports. Well, now I think OpenAI just hired a bunch of financial advisors, experts, but they hired them as annotators. So what they're doing is they're giving the GPTs all these problems, right? And about finance, the GPTs just generate the reports, then these experts review them. And they'll get, again, 3 versions of them. And they'll say, well, this one is better. And that's how the GPT, over time, it's going to become a really good finance person, AI financer. Does that make sense, guys? So that's where this evolution comes in. So it's almost like initially, which is actually, that has been kind of the common theme in deep learning in general. With images, it was the same. Initially, you created the filters. Humans would go in, create the filters, apply the filters to the images, and then you'd get some good performance. What happened when you created CNNs? Well, with CNNs, now you had the structure of a filter, but the values of the filter were learned by the neural network, and then the performance was way better, right? So it's almost like you always just can let the neural network or the deep neural network figure it out. And by using clever techniques, and one of the most clever ones was reinforcement learning. So here, somebody is actually trying to create this special architecture like a BART, and it turns out, a GPT can do it with the right technique. Questions? Yeah. So let's read through this one just briefly. So we present BART, a denoising autoencoder. So like I said, I'll cover autoencoders for sure. Very basic one that we can train from scratch. So we present BART, a denoising autoencoder for pre-training sequence-to-sequence models. BART is trained by corrupting text with an arbitrary noising function. Yeah, so that's kind of an autoencoder. And learning a model to reconstruct the original text. It uses a standard transformer-based neural machine translation architecture. So despite its simplicity, it can be seen as generalizing BERT, GPT, and many other more recent pre-training schemes. So yeah, so I would describe it as almost like the original transformer, right? They're saying that it includes both a BERT and a GPT, which is essentially saying it includes an encoder and a decoder and some other arrangement. Do you guys see that? But actually, GPTs like ChatGPT are only based on decoders today, and that has been like the amazing thing. It's almost like it was created for some task, and then it was discovered that it was this really powerful thing. Okay, yeah, reinforcement learning is certainly, that's why we're going to cover it in this course. For training, it's a nice technique for fine-tuning and training deep neural networks. Okay? All right, so that was a BART. Let me close this. So we did this one and we summarized. Obviously, we know that we can get better summarizers, right? So that was the question. All right, so let's move on to the next example. So I'm here in intro. Let's see, so the next one I have here is book example 1. Yeah, so this is another type of a BERT. So I'll do this one again, just to kind of give you some insight. This is, more like a traditional, so it's a BERT based on case. So that means it's a BERT model, like the original BERT, a base model, and on case means that it just uses lowercase, right? So that should be the output, I think. Yeah, they're all lowercase. So back then they were playing with this idea, what if we don't use uppercase, what happens, etc. So we'll try this one out. So here you can see from transformers, we have a BERT tokenizer transformers pipeline, this auto model. Okay, so we add the libraries. Okay, BERT tokenizer, so from pre-trained, BERT based on case. Here's the text. Remember, the text needs to be converted to embeddings, right? Think of it as a dictionary, right? So we run that. Okay, so there is, if you guys remember, we did all of this. For those of you that haven't taken 520, we'll cover that in 520. But if you remember, every word here, like the subword, gets converted into a number, and then that number through the NN embedding gets mapped into the embedding. Make sense? Okay, so this just converts the text into these IDs, right? These integers. Okay, and now we are also, because we're using Huggingface, we have this format, right? So this is the thing that I was saying. We're going to have to get used to these formats of having a mask, the type of ID, the IDs themselves, and so on. So we'll talk about that later. Sometimes this can be a little bit specific. All right. And now let's do the encoded input again. So tokenizer takes in the text, which is using transformers is easy, and we can just represent this, and that's the IDs, the number representation of the text. All right, and this should be kind of the same idea. We're gonna run, from auto model, we import from pre-trained BERT base on case. This is a BERT pre-trained model. We assign it to a model variable, and then this encoded input goes into model to produce an output, right? So we click on that. And you can see it's still just a tensor of numbers, because think of it as not having a head. The pipeline will provide the head that we want to use so that we can do a task, okay? And this is one of the ways that transformers works. There's been a lot of development in transformers, although it's a very stable library, I should say. So it's nice that way, but you'll see other ways in which we can do things later. All right, now, so that's the tensor. Now we can conveniently just use the pipeline again. Okay. All right, so pipeline fill in mask, BERT base on case. And then I have the variable on masker. I'm going to give it a sentence and print it out. So there it is. So the man worked as a carpenter, waiter, barber, mechanic, salesman. What do you notice about that? This was the original criticism of large language models, right? They have bias. Are they bad entities? No. They were just trained on data, so they're just a representation of the data that they saw, which actually is kind of like your initial question, right? So it's saying that men are mostly carpenters, barbers, mechanics, salespeople. You see that? So there's text has definitely large language models will capture bias because they're machine learning algorithms are biasing machines. That's essentially what they're learning. They're learning like statistically, right? The correlation between words and what's more common, like what two words go together, right? So it's going to learn that. Okay. So yeah, so this is an example of that. Any questions? Is there anything you'd like me to try here? So here's an example. Huh? Two missing words? We can try it. I don't know if it'll work. The man worked as a and went to, let's see what happens. The doesn't seem like it wants to, can do two, at least this pipeline. Or maybe it's the form, let's see. Well, here it is. The man worked as a carpenter and went to, worked as a clerk. Yeah, so it's not like, it's probably not correctly formatted. I'd have to think about this. It's nice how this is showing a lot of things, right? So everything that's going on behind the scenes, it's got all these special characters like CLS, etc. So we'll see that later. It's possible, which I do think when these models were trained, they only had one random word. So, but let's try another one. So that was book example 1. Got Electra. So this one we can just look at because it's kind of similar. So here's another example. There's another version called Electra. Again, from Transformers, import Electra tokenizer. Got the pipeline example again. Not everything is going to be pipeline, right? But today I'm trying to keep things simple. So then Electra tokenizer from pre-train. Notice this is being downloaded from Google. So Electra, notice it says small. So this might be like a smaller version. Then, of course, we have pipeline, film mask, model, Google, Electra small, generator, and the tokenizer. Similar approach. And then we give it a sentence. We invoke film mask, and then we can say the goat on the mountain will, and you can see here, will die for some reason, feed, eat, be, and survive. Yeah, so pretty simple. Notice here also from the tokenizer, if I want the mask token, it tells me what it is. So remember that. So this is an object, and there's a few special words that are used. Okay. So what was that? Electra? Entailment. So we're going to do actually 2 examples of this. So let's take a look. So this is a little bit different now. We're going to get into this example is nice. I have 2 versions of it. This one doesn't work that well, but the second version does work well. So remember in your first machine learning class, right? You were taught, let's build a classifier. So you'd have inputs and the label, have to do all the training, right? Measure performance, all of that hard work. Well, everyone that learned machine learning had to do that. And then once they had large language models, they were like, do we still need to do that? What if we just use LLMs as classifiers? Do you see that? So here then they started to build that pipeline. So here we have from Transformers, we have this object called auto model for sequence classification. So it's essentially, again, some model like a BERT, right? It's got the tensors, all the embeddings. You get to a certain embedding, and then you add a head. But now this head, instead of summarization or filling in the mask, will do classification. Do you see that? All of it, of course, we could code from scratch with actual neural network layers, but, we have these constructs with the transformer. So that's what we're going to look at. I'll do this example. This one, as I said, didn't work as well. My second example does work a little bit better. And this actually also, you'll see later, is something, make a note of this, because this idea can be used for the first homework assignment where you're going to train a BERT model as a reward function, okay? So the homework, I think, is I'm going to ask you to get a BERT from the Huggingface hub, download it, use that, but also use an approach like this one, okay? So let's start looking at it. Here it's called entailment, but it's really like a classification. So let's think it through, all right? At least the idea. So I have from transformer, again, pipeline, keeping things simple. Then from transformer, auto model for sequence classification and auto tokenizer. Okay, so I have those 2 objects. Then I'm going to go over here. I'm going to use CPU for this, for the inference part. So I'll set that up. I'm using CPU anyway. And here is, sort of the idea. So why is it called entailment? It's, it was like the fancy term used in research when they had competitions and things like that. I think they called that part of the competition the entailment competition. So it's like, what does this entail? It's a type of a classification. That's where it's kind of coming from, but it just became like a classifier with LLMs. So here, I have a sequence. I'm going to France, right? So that's the sentence. And then three labels. So essentially, you can see the idea here. The LLM should say if this is a sentence related to travel, cooking, or dancing, right? What does this sentence entail, essentially? So I'm going to do that. So then, we can use transformers, the transformers library, to kind of create a pipeline for this. And the advantage is we're using a pre-trained model. So in this case, notice that we're using one from Facebook. So it must be a very powerful one. It is, in fact, a BART large MNLI, right, model. So again, as usual, we have a model and a tokenizer. But notice that it's going to be with auto model for sequence classification, which, like I said, means the head, that's being provided is specific. Okay, and the tokenizers. So I have these two models. There they are. You can see 1.63 gigs. Okay. Yeah, give it a second there. So how can I put this? So imagine somebody before this class, right, and you don't know anything about transfer learning, and they say, I want you to build a model that you give it some text and you classify it as something. So what would you do? You'd probably collect a whole bunch of like paragraphs, start reading through them, give it a class, spend like a week doing that, and you end up with maybe 2,000 samples, right? And then you would go ahead and try to build a model and do all this work. That's student A. And then there's student B, and student B is like, you know what, I'm just going to use transformers. I'm going to take an LLM and use this technique, and it's going to take me 30 minutes. And probably my method will be better, too, because I'm using an LLM. You see that? So that's what this gives you. You should definitely use these approaches. Okay. All right, so because it's just way more powerful, right? Here, you're actually solving problems. Over there, you were learning how to build a classifier. Sometimes, though, you can, like in an industry where now if it's a language problem, you have a whole bunch of LLMs. If it's an image problem, you have a whole bunch of resonance, right? But if you go to a factory, steel furnace, then you don't have any pre-trained or fine-tuned models. So there, you do have to build it from scratch, right? But for this field, take advantage of what you have. Okay, so let's see what we do now. So I've created a model and a tokenizer. All right, so now this is how it works for this example, because it was entailment. So this is how they did it. So you would create the premise, which is the sentence, and then the hypothesis, which this example is. You give it the labels, which are 3, right? And in this format, then you give the whole thing to this particular Facebook model, which I don't think is that good, to be honest. But as you can see, I can print it. So premise, and just in the interest of time, I would print these, and it would be the sentence. Notice that the hypothesis includes the list of classes. So now what you do is, for this example, is that you are going to tokenize this. This tokenizer takes the premise and the hypothesis in this specific format. Right? So tokenizer.encode takes the premise, the sentence, the hypothesis with the 3 classes. This we have to change to true, I think, if I remember correctly. All right, and then run X. What did I... I had, I did get this error before, but I think I just changed that to true. Yeah. Oh, okay. I see. It's without the. Boolean, I think. Was it just truncation? Okay, thanks. All right. No. Yeah. All right. So that worked. Okay, great. So, uh, there we are. All right. So we do that. Tokenizer encode. And then now we give this X to the model. So the model just has this very specific format. So you can see how this is kind of like historically, right? This is when they were starting to apply this technique. In the second example, I have a much easier, much more effective way of doing this exact same task. But here I take the premise, the hypothesis, this all put together, and now it's given to this Facebook NLI model, right, which is an auto model for sequence classification using a BART model. So it's quite a bit going on here. And it's supposed to give us like the logits for these three classes, which are these. So I'm just going to type logits. Let's give it a second. And there it is. Does this make sense, guys? So what is this giving us? It essentially is giving us like a probability distribution for the three classes. So we would take the best probability. Got it? Do you see that? So I do this example just to kind of show you the evolution of this. There's a better, don't use this one, use the next one, but then we would have to choose the probability. You can see you can play with it and then, choose the class. All right. So, but the fact that this is using a BART model, I'm not saying it's like a terrible idea, but it's just in the evolution, we want to probably move on to something else. All right, so now let's try. So we did that entailment. Then it should be, I think it's this one. This is now called, yeah, it's the same example. So now the new term, before it was entailment, now it is just called zero shot classifiers. I'm pretty sure if you guys take, maybe in your generative AI class, you'll do prompt engineering. And even in prompt engineering, you can do zero shot prompting, right? So essentially, you give the prompts to ChatGPT, and ChatGPT will get it, and then it'll give you the answers, okay? So in this case, but yeah, the terminology is zero shot. This is important. As I said, make a note of this because in the first homework, the BERT reward function, I'll probably suggest get a BERT model from the hub, but also build a zero-shot classifier that is a type of a reward and compare both to see which one might be a better reward model. Okay? So the first homework is very easy. I'll ask you to download a GPT, and then it'll generate text given text, right? And then I'll just ask you to nudge it to be more, like funny or more romantic, something like that, right? So now, given that it is a GPT-2, it's not going to be that great. Don't expect that the answers are going to be great, but we can still see the difference. You can still see, oh, this is the original answer, and this is the answer after reinforcement learning through this BERT reward function. And we'll know it work. We will know it worked because it'll have like more romantic words, right? So, the original answer versus the new answer, you'll see like that, or it'll have more funny, some funny word, or also you can make it more like spam. And so, you'll have the original answer or you'll have the new answer, which might have something like cash, free cash, click here, something like a common. So that's what you can expect here, is that if you're using something like a GPT-2, the answer looks terrible, but you can still see the difference after you've applied the reward function. Okay, so I'll talk more about that later, but because we're talking about this zero-shot classifier, I want to connect it to the first homework. Okay, so yeah, so really a reward function is something, as I've described, you can use a BERT, it takes in text, so we know that a BERT would produce an embedding, but there's no reason why we can't take that embedding, add a head or a few layers, and just make it predict one value, right? And so that's kind of what this is doing, if you think about it. So let's see how that would work. So notice I'm going to do the zero-shot classifier. So now I'm going to use this object here. So pipeline auto model for sequence classification. Here it is. I'm using pipeline instead of that whole entailment thing with the premise and the sequence, right? So pipeline is much more robust. And it's got this functionality of specifying that I want a zero-shot classification. I'm using from Facebook a BART large MNLI classifier. Okay, so it's got a green check here. And now notice that this is much simpler to set up. So the sequence to classify is still the same one. I'm going to France. And then we have the candidate labels, travel, cooking, or dancing. So this, I think, performed better when I did it. So let's see. So notice that now we have this, the classifier pipeline. So I give it the sequence to classify and the candidate label. Do you guys see that? I run it. Remember that this is a pre-trained model. Okay. And now, if I print the result, okay, so let me grab this. Control copy. All right, so let's take a look. So it returns it obviously in this Huggingface type of format. We've got the sequence. I'm going to France. Got the labels, travel, dancing, and then it simply just provides some scores. What do you guys think? Is it good or bad? Pretty good, right? So now it's set that it's travel. So again, I go back to this thing, student one never knew about transfer learning. You give them that problem, probably get some paragraphs, label them, build a 10-layer neural network, train it, that's it. Student 2 just gets a pre-trained model, whatever BERT, BART, whatever it is, uses Huggingface, transformers to format things a little bit. That's the one, the learning curve is learning that. But look at how effective the model is. And you can do this for lots of other things, right? So here we said travel, dancing, and cooking, but you can change the labels to be something else. Doesn't amaze you? But yeah, so yeah, right. So and that's what I was saying about sort of like here, you can actually solve problems, right? Before you're building great models, might be pretty good, but if you leverage pre-trained models, you can accomplish more possibly, right? The only downside, as I said, is that the models are pretty big, so you have to deal with that. Any questions, guys? All right, so I think we have some time left. Let me just today, it's just the first day, just kind of to show you some of the things that we can do. This is just inference. So we did the zero shot. This one, as I said, is important. Later on, let's say, just to kind of to give you an idea here. Let's say that you want to build, let me see. Let's try something a little bit different. We have a little bit of time. Let's see if this works, okay? So I have a smile on my face today, right? Okay, and then I'm just going to have two classes. Whoops. Happy and sad. Do you guys see that? Okay, let's just try it. I haven't really tried this, but let's see. So I have my classifier. Okay. I have this. Did I misspell something? Got that. Okay, got a green check. Okay. All right. So what do we have? What do you guys see? I have a smile on my face today. The two labels were happy and sad. What do you think? Is it correct or incorrect? It's correct, right? And you see, I'm just trying something, and I can do 20 of these, right? So now think about it. I'm giving this model text, and what I get in return is just a score. Now I'm getting two scores, but I could easily just ignore one of the scores and then just focus on the other one. So essentially then, let's say for instance, that I just want to focus on the sad score. So I can ignore happy, just ignore it. This is 0 index, this is 1 index. And now I can give this model text, any, different examples of text. The text goes in, and this value, you agree that it's going to change, right? It's going to sometimes, here the value is 001, but maybe if I use a sentence like, I have a tear maybe on my face today. Let's look at what happens to this score here. That didn't work. I am crying. I am crying today. See, is this correct? I'm crying today. All right, let's try it. Let's look at this score here, right? Oh, I forgot one thing. Notice that it's changing the order of so in the previous one, I think it actually did work. I forgot about that, and that's actually something you have to be careful with when you use this technique. So let me go back to the previous one. So I have a tear on my face. I have a tear on my face today. Sad, yeah. By default, it changes the order of the labels, right, in order of the probability. So that's an important thing to watch out for. So it's not the index. Actually, just, I don't know. You have to figure it out with code. But what's important here is this is a BERT, which initially was designed to take a sentence, fill in the blank, and produce the missing word. From there, they remove that head, and they just let it create an embedding. And then they change that head to one that just produces a vector of 2. Do you guys see that? If I ignore one of them, then I just essentially now have a BERT that takes text and just produces one value, a score, from 0 to 1, which is telling me how sad, I am. So then now think about how you can use this as a reward function. You have a GPT, you want to make it sadder, right? So you give it text, it generates text, then that text goes into this function, and this function is always telling you, well, I read this text and I think it's a 0.6 or a 0.5. Do you see? So it's giving you a scale of sadness. And then that information can be used with reinforcement learning, right? Through human feedbacks, it can be used to update the GPT to make it sadder. Does this make sense, guys? Obviously, there's going to be a whole framework that we have to add to this, so it's not just going to work like this. We'll have to import something else from transformers that allows us to connect those two models so that the feedback can go back to the GPT. But essentially, that's the idea. So now, instead of, we could have a human, right? And a human gets the output text, reads it, and says, oh yeah, this is sad. I'm going to move like the scale. But, it takes a lot of effort to do that. It's expensive. So then they figured out that they could actually automate that process a little bit. Let's say, for instance, instead of having 100,000 human annotations, they just do 5,000. Use those 5,000 to train a BERT model, and then that's it. Got it? So this is how they've solved a lot of problems. So again, this was just an example to show you that, first of all, we can do a classifier. We can build a classifier for just about anything that we want using a powerful LLM. And then we can then just select one of the two categories, right? And use that information to nudge the text to be sadder, happier, funny, toxic, whatever, untoxic. So if you think about how they've tried, for instance, to make text be less toxic, less biased, same approach. Right? You get, take text from 4chan, very toxic, right? So then you train a model to look at 3 things and say which one is the least toxic, and then you use that information to update the GPT. Got it? All right, so we'll come back to that idea. Today I'm just making the connections, all right? But really important to understand that we can create classifiers just by taking this approach. All right. Are there any questions on any of this? All right, great. So I have 9 minutes, so I'm going to wrap up going back to the PDF and just kind of introducing some of the definitions, okay? And that's kind of the intro for the course this week. And then next week, we'll move on to something else. I'll probably start thinking about assigning the first homework next week. All right, so let's go back to Brightspace. Go back to transfer learning. So, like I said, this course is about deep learning, building, practical, because as you have seen, you can now build very powerful classifiers, and it's very easy to do it, but we have to take advantage of, when we're using these very deep neural networks, we really can't train them. I mean, that's the reality of it. They're just too big. There's too much data. But we can borrow someone else's weights by using transfer learning. So let's take a look at some of these details. So I provided this PDF here. So let's read through it. So transfer learning. So transfer learning is one of the most important developments in AI since transformers. Transfer learning is an approach where you pre-train a model with some data, usually a lot of data, and then fine-tune the same model with less data, but for a specific task. Okay, so usually we're talking about, terabytes of data versus megabytes of data, something like that. This allows companies or entities with vast resources to pre-train models such as Facebook, Google, etc., that they can later share with others. And they're shared via, as you have seen, the Huggingface repo or other places. There's other places where you can get these models. Training with massively large data sets requires a lot of resources such as computing power, money, and can currently only be done by large institutions and companies such as Google and Meta. OpenAI can do it, but they rarely share their models. Okay. So some of the important ideas in transfer learning, some of the most important ideas include the concept of pre-training, right? Fine-tuning, freezing some weights of the neural network. You guys have done this in 520 with the neural input optimization. Sharing the weights from one model to another. That's essentially what we're doing. So if you think about it. So all you're doing is you create the architecture, right, in your own environment, and then somebody gives you a file with the weights, and you plug those weights into your architecture. Obviously, you have to make sure that you have the exact same architecture that they had. If you get even just one error, everything can corrupt. Okay, so you have to get that exact. So I heard someone was talking about C, for instance. You can train a model in Python, right, and then code that same architecture in C, and then you can take the weights that you train in Torch and plug them into the C architecture, for instance. And it should work, right? So as long as you get the formats and everything correct. So sharing the weights from one model to another is important. Another concept, as I have mentioned, is reinforcement learning through human feedbacks. So I've given you some of those concepts. I'll share this paper later. And obviously transfer learning metrics. So there's going to be some metrics that we can use. So pre-training is the process of training a model like a large language model on massive amounts of data. In the past, the best models have been the ones pre-trained by Google, OpenAI, and Meta. Pre-training starts with a model that has had no training and where the weights are usually initialized randomly. So this is, like 520, building any machine learning model from scratch. You have random weights, you start to train. That's what pre-training is. The process can take many months, require multiple thousands of GPUs, and training needs to be performed on distributed GPU systems. This is quite complicated to do. You start with code such as that of the GPT algorithm, but you need to train the model for long periods of time with lots of data. All right, so we've seen already that if, like in the last example, we were using a pre-trained model on massive amounts of data, and it performs really well. Now, fine-tuning. I haven't shown any examples of fine-tuning. This will be the kind of training that we do in this course. Fine-tuning, and we can do that with images, we can do that with text. Fine-tuning is the process of taking a pre-trained model with pre-trained weights and performing some additional training on it. It's like we train it for a while, pause, and then there's a second training. And that's the one that we do. In our case, we're going to bring down a pre-trained model like a GPT-2, and then now with our data, we can fine-tune it, for instance. Here you want to reuse as much of the pre-trained weights as possible. One scheme for this requires freezing some layers of the network so that the corresponding weights are not changed during fine-tuning. So, you can freeze some of the layers and then maybe you just update usually the last layers. So that's one approach. Another approach is to have, during pre-training, the learning rate is, higher, whereas with fine-tuning is a much smaller learning rate. So that way smaller learning rate means smaller updates. So that's another approach. Do you see that? So there's several ways that you can tackle this. But yeah, one scheme for this requires freezing some of the layers. Fine-tuning can still be done on one GPU, and that's the nice thing here, right? So whereas to build a really good LLM, to pre-train to an LLM, we really, with a lot of data, we really need a lot of GPUs. But fine-tuning can still be done with just one GPU. So and with 100,000 samples of data, right, instead of trillions. So that's a really good thing. So fine-tuning can still be done on one GPU currently, and may not require massive amounts of data, because it is usually focused on specific tasks like sentiment analysis, question answering, etc. And then here's an example of freezing some weights. This is just to show you freezing some weights of the neural network. So this is in PyTorch. When performing fine-tuning, freezing part of the weights of the model may be required. This process can be seen in the next code listing. So here's an example where you freeze the first 70% of the hidden layers, right? So you can see, for instance, you grab this model GPT dot transformer dot h, which will contain all the hidden layers. You see that? And then that you call that layers. You can count them, so you can see there's 12 layers here. Then you just 0.3 times num layers. That gives you the number of frozen layers. 7, so it's like 9 or something like that, right? And then notice how simple it is. 4-layer in layers to num unfrozen, right? So we just do the first 70%. So we grab the layers and we say layers dot requires grad equal false. Does this make sense, guys? So out of 12 layers, we're iterating through each one. And if it's from 1 to, let's say, 8, we set the requires grad to false. That means that the weights of that layer will not be updated. Questions? Yeah. So this is if we were doing this from scratch. Obviously, because we use transformers, usually we won't have to do it this way. There will be some kind of flag or something like that that we can set. But the underlying approach is similar to this. Okay, and then we just print the layers. So now we can look at it. Notice that in the previous code listing, we iterate through all the layers and change the parameter requires grad to false for all the layers we want to freeze. And then the result for a GPT-2, so notice this is the result of freezing can be seen below for a GPT-2. So notice this GPT-2 then has 12 hidden layers. 12 layers. So you can see that here. Notice it's got, there's linear layers, attention layers, so everything, right? Like the blocks. And it's showing this is, this is set to false, this is set to false. Yeah, and at I think I have these little dots here, so I didn't put all 12 layers. But it just means like this is the beginning, they're all false, from 0 all the way to 8, false, and then after that they're true. Do you guys see that? So this is one approach of fine-tuning that we can take. And the idea being that you do want, like the first 8 layers have more to do with like understanding grammar, understanding if something is a noun phrase, a verb, a determiner. And then once you get into the last layers, now it's looking more at like the semantics, the meaning. So it's, so you want to retain that knowledge of finding nouns, verbs, etc., right? So that's why you freeze those layers. And then it's only after like the 8th layer that you start to update the weights a little bit. Got it? All right. So this is just an example to give you intuition. Yeah, and so it is 9:22. I'll do these because there's quite a bit here. I'll cover these in the next class. All right, so it's 9:20. So we can end the class here for today. Yeah, so welcome to 5:30. As I said, practical deep learning, and we'll continue next week. All right, have a good break, guys. No homework this week. Maybe next week. Make sure to sign in, please, if you haven't done so already.